Hello and welcome to Data Science for Everyone. Today I'll be teaching you regular expressions in Python. Before watching this video, I highly recommend you to watch my previous video on string manipulation. The link is in the description. Let's get started. This time I have prepared a full report with the code that I have used in this video as a PDF document. If you want the document, please give me your email IDs in the comment section and I'll send it to you. Before I begin, I'd like to request you to please subscribe to my channel and like my videos if you're learning from them. With that, let's learn regular expressions. A regular expression or regex is a string made up of regular and special characters used to describe a search patterns in text. That might sound complex, so let's break it down. Let's look at an example of regular expression. The R before the string indicates that it's a raw string. Inside the quotes, we can see that there are special characters such as \d and integers within curly braces. We'll look at what these special characters mean in the next few slides. By the way, this pattern inside the quotes helps in matching US Social Security numbers. We'll be using a package called re for our tutorial today. To search for all matches, we'll use a method in re called findAll. It needs two arguments, the pattern and the text to search. Let's look at how to find normal characters. We start by importing re package, then we set a pattern to search called hi and append r in front of it. Then we call the findAll method with the pattern as the first argument and the string to search on as the second argument. We can see that there are two instances of lowercase hi in the string and both are returned. Notice the hi with uppercase H is not returned. Regex also uses special characters called metacharacters. These represent categories or types of characters. One example that we looked at before is \d, which stands for any digit. If we use it on a string that contains digits, it will return those digits as shown here. \D on the other hand will match all non-digit characters, unlike \lowercase d as shown here. Another example of metacharacters is \s, which matches any white space characters like spaces or tabs as shown in this example. On the other hand, \uppercase s matches any non-white space characters, which we show here to match hello world with a dash in between. \lowercase w is used to match word characters and \uppercase w is used to match non-word characters such as spaces, tabs or special characters as shown here. Now let's look at quantifiers. If we see curly braces with digits such as 3 and 10 after a word character, it means that the regex will match characters at least 3 and up to 10 times. In the output, notice that the uppercase X is not returned since it has a length of only 1. If you remember, I had shown you this example for finding SSN-like features in a string. The regex matches patterns with 3 digits followed by a dash, followed by 2 digits and so on. As you can see, it only returns the right match, which is the second part of the string stored in a variable called pattern2 and does not match the first part. Let's look at another example. This code is using a regular expression to find all matches of a specific date-like pattern in a string. Here, the regex will look for dates formatted as full year, followed by a dash, and followed by a 3-letter month. \d4 matches exactly 4 digits, for example 2025 or 2024. Dash matches a literal dash. Uppercase and lowercase a to z followed by 3 matches exactly 3 letters for both upper and lower cases. If we want to split a string based on a pattern, we can use the split method. In this example, we split the string at every exclamation mark and it gives us a list of separated words. To replace patterns with something else, we use the sub method. It takes a pattern, a replacement string, and the original text. For instance, we are replacing every occurrence of the word blue with green. Now that we have a strong foundation, Let's learn how to detect repeated characters using regular expressions. Suppose we want to check if a string meets a specific criteria. This pattern matches a string with the following criteria. The \w8 matches exactly 8 word characters. It could be uppercase, lowercase, or an underscore. And \d4 matches the previous regex followed by exactly 4 digits, which is from 0 to 9. Let's demonstrate with an example. To find this pattern, we can use the search method from the repackage, which takes a regex pattern and a string as arguments. It checks if the pattern exists in the string. We can see that the first string exactly matches, but the second one does not, and therefore the second returns none. Now let's extract dates from a string. Each date has digits, followed by a dash, and then more digits. This means that we can match one or more digits before and after the dash. We use the plus quantifier to do that. The plus quantifier matches multiple unspecified number of digits instead of a specific number that I have shown previously using curly braces. Let's say we're working with social media data and we want to extract usernames from a piece of text. These usernames always start with the @ symbol and may contain special characters like underscores or punctuations. Our goal is to write a regular expression that finds them. Let's break down the regex. The @ symbol matches the actual @ sign. \w+ matches one or more word characters, which includes letters, numbers, and underscores. As we can see, the usernames are extracted from the string. The question mark quantifier is used when a character may appear once or not at all. Imagine we need to match the word color, but also account for the British spelling of color with an U. When we write the regex $R, it makes the U optional. This gives us both versions in our results. Quantifiers only affect the character that is immediately to its left. For example, in the pattern BYE+, the plus quantifier only applies to one or more E characters. That's why it doesn't match the S's after the by. Now let's go over some more meta characters that are especially handy when working with regular expressions. We'll start by exploring two useful methods in the re module, search and match. Both helps us find patterns in text using regular expressions. For example, suppose we want to find a sequence of digits in a string. If we try both search and match with the same pattern, they behave a bit differently. While search scans through the whole string to find a match, the match method only checks at the very beginning of the string. In this example, we see that search was able to find the numbers 1, 2, 3, but match was not able to, since 1, 2, 3 is not at the beginning of the string. The .meta character is used to match any single character. Let's say we want to detect website URLs in a string. We know that they start with www and end with com. So we can create a pattern that starts with www and ends with com and allows for characters in between. Since we don't know how many characters appear in between, we can use a dot followed by a plus sign, which means match one or more of any character. This way, our regular expression can successfully detect complete URLs. The caret is used to anchor a pattern to the beginning of the string. In this example string, if we search for a pattern that starts with the followed by a space and 2 digits and then a word, we'll find a couple of matches. But if we add a caret in the beginning of our regex, only the pattern that appears right at the start of the string will match. On the other hand, the $sign anchors the pattern to the end of the string as demonstrated here. What if we want to search a literal character like a dot or a $sign? These symbols already have a special meaning in regex. For instance, if we want to split a string wherever there is a dot followed by a space, we might write the pattern as just dot and space. But this won't work as expected because the dot has a special meaning in regex already and will match any character. To fix it, we need to escape the dot with a backslash as shown here. This tells regex to treat the dot as a literal dot and not a wildcard character. Now let's look at the OR operator. Suppose we want to find the word book in a string, but it might appear as book with uppercase B or lowercase b. In this case, we can use the OR operator, which is a vertical bar. It allows us to match either variant, so our regex will match both the uppercase and lowercase versions. We can also use square brackets to create OR conditions within a regex. Let's say we're looking for a pattern that starts with any letter, uppercase or lowercase, followed by a digit. We can write it as shown here. This regex extracts any combination of upper and lowercase letters followed by a digit. Running this regex, we'll find all such sequences in a string as demonstrated. Imagine we want to replace all special characters in a string with spaces. We can define which characters to look for using square brackets as shown. This tells regex to find any of these characters. When a match is found, we can replace it with a space using the sub method, resulting in a version of the string with spaces. We have worked with repetition quantifiers before. In this part of the video, we'll dive deeper into how these quantifiers behave during matching, and we'll discuss greedy versus non-greedy matching. There are two main ways quantifiers try to match patterns: greedy and non-greedy, sometimes called lazy. The quantifiers we have seen so far, such as a star, plus, or question mark, are greedy by default. Greedy quantifiers try to match as many characters as possible. They always aim for the longest possible match. For example, if we look for one or more digits in the string in this example, a greedy quantifier will try to match the entire sequence. It starts with the first digit, which is 1, and keeps on going until it cannot find any more digits. Greedy quantifiers use a process called backtracking. If they grab too many characters and the rest of the pattern doesn't fit, they give up characters one by one and try again. Think of it like exploring a maze. If you reach the dead end, you backtrack to the last fork and try a different path. For example, with this pattern dot star by on the string z by AAAA, the greedy quantifier grabs the whole string first, but cannot match the A's at the end of the string. So it slowly releases one character at a time until it finally matches by. Non-greedy quantifiers, on the other hand, try to match as few characters as possible, returning the shortest match that fits. We can make a quantifier non-greedy by adding a question mark after a greedy quantifier. For instance, with one or more digits on the text, the non-greedy quantifier stops right after the first digit, which is 1, because that satisfies the condition. Non-greedy quantifiers also backtrack, but in the opposite way. If they match too few characters and the rest of the pattern cannot match, they expand the match by one character at a time and try again. For example, using the lazy quantifier dot star question mark by on z by AAAA, it first tries to match nothing and then adds characters step by step until it finds z by. Now let's explore some advanced ideas, specifically how to use capturing groups to extract parts of a match. Imagine we have this sentence saved in a text variable. Anna has 1 cat, Mark has 2 dogs, and Lucy has 3 birds. Our goal is to pull out the details about each person, their name, how many pets they have, and the type of pets. For example, Anna, 1 cat, Mark, 2 dogs, etc. Since the sentence follow a pattern, we try a basic regex. Any uppercase or lowercase letters followed by whitespace, then any word character followed by whitespace, then a number followed by whitespace, and any other word character. The output looks pretty good, but it still includes the word has, which we don't want. Let's fix that. We start by focusing on only capturing the names. We add parentheses around the part of the pattern matching the names to capture them. This lets us extract just those groups, which in this case are names, from the matches. In the updated code, parentheses wrap the name section. When we run it, only the names appear in the results. Now let's capture all three parts together: the name, the number, and pet type. Each set of parentheses define a group, and each group gets a number. Group 0 is the whole match. Group 1 is the first set of parentheses. Group 2 is the second set of parentheses, and so on. We'll see why these numbers matter soon. Looking at the code, parentheses surround each group we want: the name, number, and pet type. The output is a list of tuples, where each tuple has 3 elements, each corresponding to one captured group in order. Besides extracting data, capturing groups help organize it. For instance, from our example, we can access the pet type separately using indexes, just like with lists. We have seen the vertical bar or pipe operator before. Imagine we have a string listing some fruits. If we want to find out the occurrences of either apple, banana, or cherry, we can use the pipe to separate these options. This will give us a list with all 3 fruits found in the string. Now suppose the string includes quantities like 2 apples, 1 banana, 3 cherries. We want to match the fruit names only when they follow a number and a space, like 2 apples or 3 cherries. At first, it seems natural to try grouping them with the pipe operator. However, the Regex engine interprets this differently than intended. It reads the pattern as either a number, space, and apple, or banana, or cherries. This means that banana and cherries will match anywhere in the string, even without preceding a number and space. To fix this, we use alternation with parentheses to group the numbers and the fruit options together properly. Now the Regex look for a digit and a space followed by either apple, banana, or cherry. This way the matching works correctly and we capture the number and the type of fruits. Now let's explore how we can refer back to capturing groups within regular expressions using backreferences. Suppose we have a string with the date. We want to extract just the year, month, and day as separate parts. To do this, we wrap the parts of the Regex pattern in parentheses, which lets us capture those sections. As we have discussed before, each capturing group gets assigned a number. The entire match is group 0. The first set of parentheses is group 1, the second is group 2, and so on. Using a search function, we can pull out these groups by calling the group number. For example, group 2 would return the second captured part, which is 11. Group 0 returns the whole matched text. The dot group can only work with search and match methods. We can also label capturing groups with names for easier access. Inside parentheses, we can use the syntax shown in the code, giving that group a clear identifier. With that, we have come to an end of our tutorial on regular expressions in Python. Remember to like, follow, and subscribe to our channel, and also let us know what other topics we should cover. Thank you.